Ask a junior engineer how they approach a problem. They will immediately start describing the solution. Ask a strong senior engineer the same question. They will start by asking 3 or 4 questions about the problem first. Because experienced engineers know something important. If the problem is unclear, the solution doesn't matter. Many projects go wrong not because of bad coding, poor architecture, or lack of effort. They go wrong because the team solved the wrong problem. The code works, the feature is complete, but the real issue remains unsolved. In this chapter of the Engineering Judgment series, we start with the most important foundation of good engineering: defining the right problem before trying to solve it. Because the quality of your solution will never exceed the quality of the problem you are solving. Start with the real problem. Before touching design, architecture, or implementation, the most important question is, what problem am I actually trying to solve? Not what feature was requested, what ticket exists in the backlog, but what real-world problem is the system meant to address, and why it matters. Framing the problem clearly prevents wasted efforts, misaligned features, and technically impressive but ultimately useless solutions. Invest time in getting the problem right before trying to solve it. Here is an example. A team receives a request: add a dashboard to track customer churn. The obvious response is to start designing charts, metrics, and reports. But when the team pauses and goes deeper, they realize the real problem isn't lack of dashboards. It's that customers are leaving because support tickets take too long to resolve. Building a dashboard would show churn more clearly, but it wouldn't reduce churn. The real solution might be improving support workflows, speeding up response times, or fixing the root causes of customer complaints. By starting with the real problem instead of the requested feature, the team avoids building something impressive but ineffective and focuses on solving what actually matters. Solving the right problem at the right level. Every system exists to solve a core problem, the primary reason it was built. To address it, the system is broken down into sub-problems or functions, each with its own goals. These are further divided into smaller components and so on. This creates a hierarchy of parts, each of which has its own specific challenges. Good engineers understand these problems at multiple levels. You must solve the immediate problem in front of you, but never lose sight of how it fits into the larger goal. Optimizing a smaller part while harming the overall system is not progress. Here is an example. Imagine you are building a food delivery platform. The core problem is help customers get food quickly and reliably. One sub-problem is assign delivery partners efficiently. A smaller part of it might be optimize the route for a single delivery partner. If you focus only on the route optimization, you might design an algorithm that minimizes travel time for one rider but ignores fairness, rider workload, or ignores overall system efficiency. That could improve a small metric while making the overall system worse. Strong engineering decisions come from asking, what problem am I trying to solve right now? Where does it sit in the larger hierarchy? And am I optimizing a part at the cost of the whole? Avoid solving symptoms instead of root causes. Fixing surface problems feels productive. Solving root causes creates lasting impact. A slow system might need caching, or it might need a fundamental redesign. Recurring bugs might need patches, or a rethink of architecture, testing, or even ownership. Strong technical judgment means asking what's causing this, not just what's breaking. If we fix this once, will it stay fixed? Treating symptoms creates cycles of rework. Addressing root causes reduces future cost and complexity. Here is an example. A team notices that users frequently report timeouts when uploading files. The quick fix is to increase the timeout limit or retry failed uploads. This reduces complaints temporarily, but the underlying issue remains unsolved. A deeper investigation reveals the real cause. The upload service is processing files in a synchronous manner. Large files are blocking smaller ones. The system wasn't designed for growing file sizes. Instead of repeatedly adjusting timeouts, the team redesigns the upload pipeline. They move processing to background jobs, improve storage handling, and add progress feedback for users. When you fix symptoms, you reduce noise. When you fix root causes, you remove the problem and prevent it from returning. Clarify constraints before designing freedom. Every engineering problem exists within constraints. Time, budget, resources, regulatory requirements, legacy systems, organizational priorities. Ignoring these constraints leads to elegant but impractical solutions. Mature problem framing starts with asking, what are my boundaries? What is flexible and what is not? Constraints are not obstacles to creativity. They shape creativity. When engineers understand constraints early, they avoid proposing solutions that will be rejected later for reasons unrelated to technical quality. Example: a startup wants to launch a real-time collaboration feature for its document editor. The ideal solution would involve persistent socket connections, real-time conflict resolution, distributed state synchronization, horizontal scaling from day one. Technically elegant, future-proof, impressive. But the constraints are clear. The team has 3 engineers. The launch deadline is 8 weeks. The legacy design does not support persistent socket connections. Moreover, 90% of users collaborate asynchronously, not simultaneously. So, instead of fighting the constraints, the team reframes the problem. The goal is not build real-time collaboration. The goal is allow multiple users to work on the same document without overwriting each other. With that clarity, they design a simpler solution. Introduce optimistic locking. Add visible edit indicators. Show version history. Notify users of conflicting edits. And defer true real-time synchronization to a later phase. The resultant system isn't the one they imagined, but it solves the actual user need within the available limitations. Because the team respected the boundaries, they built something stable, usable, and aligned with business reality. Their constraints did not limit them, rather, it made their decisions sharper. The difference between average and strong engineering is rarely technical skill. It is clarity about the problem, about the level at which it sits, the root cause, and the constraints that shape the solution. When engineers skip this thinking, they produce work that is technically impressive but strategically useless. But when the problem is framed correctly, good solutions follow naturally. Because in engineering, the hardest part is not building the solution, it is making sure you're solving the right problem. And this is only the first step in developing real engineering judgment. If you would like to see the full progression from execution to engineering authority, you can explore the complete engineering judgment framework at paragchitness.com.